Okay, Tony Mormino at the AHR Expo in Orlando at the Antec booth with Curtis. Curtis, how you doing today?
Great, Tony. Thank you. Appreciate you being here.
Yeah, man, I appreciate it. We're going to talk about, your control valves here, why they're different than typical VAV boxes. Sure. We're talking about airflow control in critical spaces.
Yep.
Okay, so we're going to go through these and show people what they are. They look a little different than a normal VAV box. So let's define what a critical space is first.
So a critical space is an application where you're doing room pressurization to control the directionality of airflow leakage across the boundary. And it's through that mechanism that we effectively control the sterility of a positively pressurized space, or we keep whatever's dirty air inside that negatively pressurized zone from getting out.
Okay.
Keep people safe in isolation rooms that way, pharmaceutical, compounding pharmacies, and clean rooms, wet chemistry laboratories. Really, these are some of the most common critical spaces.
Gotcha.
Yeah.
Now, why, if you're an engineer or contractor, you might be watching this. So look, been doing airflow control in schools for years or in office buildings for years. Why is this different than a typical, I'll say, VAV box doing airflow control?
That's a great question, Tony. So there are a few things that these types of precision valves are going to offer above and beyond a legacy VAV box.
Mm-hmm.
First and foremost is accuracy. Legacy VAV boxes can achieve pretty precise function at constant volume flow rates, but in most of these critical spaces, you're actually doing some sort of variable air volume strategy approach. And as soon as you deviate from those constant volume set points with a VAV box, the accuracy that you get is dependent on a lot of things you have no control over. So basically, these valves take away all those additional variables, and they guarantee accuracy within 5% across the entire turn-down range of the valve.
So accuracy in terms of turn-down
Yep.
and speed of response.
Speed of response.
Right? You got an operating room, you got people coming in and out all the time, the doors
Yes,
are
sir.
getting open and closed, the lab, the fume hoods are going up and down.
Yep.
So you need to be able to act quickly, and a normal VAV box cannot act that fast.
Correct. And the other really big one here, it doesn't really affect the supply side of a system, but it's more so the exhaust side, especially in healthcare. If you've ever been into, hopefully not, but we've all been probably to a hospital, and you go into a patient room, and the nurses, fluff out the sheets because you get new linens every time you go into a room. If there's a window and you see the sunbeam coming down, you see all the lint that enters, and gets airborne into the airstream. Well, folks, all of that goes through the exhaust duct, and it's all passing through your valves on the exhaust side of the system. And if you have some sort of airflow measuring device, like a crossflow sensor, which you see in a lot of VAV boxes that are employed, that stuff's going to build up on those surfaces. So if you're measuring flow and it's hitting the front of your flow sensor, you should absolutely expect some sort of form of sensor fouling.
Correct.
So these strategies avoid that, and we call that contamination resistance. They effectively are not affected by any sort of airborne lint, dander, dust, contamination.
Excellent.
Yeah.
Well, that's a good segue. Let's look at these things. They look a little different than a normal box. So
yeah.
We got Cody on the camera here.
Come
so
on this
bring
way.
it on over. We'll walk through the valves.
So this Antec Controls is a bit unique. We offer our customers a choice of the technology that they want to use for their application. So we actually have two different styles of valve here. They look very, very similar from the outside because they both utilize the Venturi shape. But maybe we'll start down here. You may not believe me when I say this, but this is effectively a high accuracy VAV box. It's a high accuracy terminal unit. And so we are measuring airflow. Maybe you can kind of see it from that angle, but there's a static pressure post here and a static pressure post here. This is our sensory organ. This is our airflow sensor. And so by measuring differential static pressure, we can correlate that to an airflow. So this valve is giving you live readings of flow throughout the duct. And some people, Tony, just love to measure flow, and we love that too.
Right.
Yep.
Right.
And so
trying to get you a little light here on the subject. So people can see these beautiful boxes here. So valves, excuse me.
Yeah. It's all good. It's all good. We hear that a lot. So
the airflow sensors are.
So if you want to even come around, Cody, if you can, we'll get kind of a moving photo here. So if airflow is flowing into the duct this way, into the valve this way, and you'll notice that there's two posts there, and there's actually nothing being measured on the front face of those posts. You have to go to the other side of the valve to see those little holes that are picking up static pressure in both locations. It's actually very strategic in terms of the placement of those posts because we pick up the largest amplification of that static pressure signal.
Right.
And this is the flow measuring solution. Maybe we'll pivot up more here up top to the Venturi valve. So this is what a lot of people call a flow metering valve. This valve meters flow. It's called a Venturi valve. And it's going to give you a little bit of additional speed and stability in terms of your controlled response. It is a little bit different from the traditional flow measuring strategies. Maybe stand back a little bit there, Cody. Awesome, thank you.
We're good?
So in a Venturi valve, you actually have two different types of movement, okay? The first type of movement is that of the cone, which has a spring mounted inside of it. So the idea here is that basically as there are naturally occurring duct pressure fluctuations in the upstream side of your system, air is flowing this way through the valve.
Get rid of the
There's going to be different forces because, a duct pressure fluctuation is just force over area. So there's different forces acting on the front of that cone, and it's going to relocate this cone to a new position based on a force balance. And it's happening mechanically. There's no controller telling it to do that. So at all times, the cone is relocating to a new position in real time based on the active force balance in that duct stream. This motion, if you come in really close, just for a quick zoom in, you'll notice that this motion is actually decreasing the amount of free area the air can flow around the cone when there's an increase in force, an increase in pressure, and it's increasing that free area around the cone when the pressure drops. And so the movement of that cone is actually holding our flow set point within 5% accuracy. So as long as the flow set point isn't changing, the cone is just metering for airflow. So the separate and the second kind of movement on a Venturi valve is that of the actuator. Okay, so the actuator is going to, I'll just clutch the actuator here, it's going to move the entire center shaft assembly for changes in flow set point. So effectively our flow set point adjustment is entirely decoupled from duct pressure fluctuation management. And this lets us test each and every valve uniquely at our factory before they're shipped to develop a position versus airflow curve. This is only possible because these duct pressure fluctuations are out of the equation, right? So basically we will test the position across the entire range of the valve, and on very, very accurate airflow stations, we will correlate those positions to flows. So for example, this position, let's just throw a number at it, is 200 CFM. And as the center shaft moves out, we measure this position to be 297 CFM. This position, let's say, is 400. This position is 500. You get the idea. All of that position is actually measured by a potentiometer that feeds back to the controller, so we know we've arrived at the position we expect.
I love it.
Yeah.
So what I think you're explaining to someone like me who I've been in the industry for 25 years, and I recently became familiar with this type of product. So pressure dependent versus pressure independent, right? So this is independent because we're going to say when we actuate this here, it's 300 CFM. It doesn't matter what the pressure is because this spring has the resistance to move this, I don't know what we call that part.
The cone. Yeah.
To get you the CFM we need. So.
Yes, sir. Yeah, so actually both of these solutions are what we call pressure independent. But how they achieve pressure independence is a little bit different. So this solution here is what's called electronically pressure independent. The idea is that you need a controller to take in that flow measurement, compare it to the set point, and then the only movement on a flow measuring solution is the actuator.
So this has an actual valve in it. So
Yeah.
Can we get a shot of that?
Yeah.
Can we show maybe the profile from the two sides here? So why would you use the pressure dependent versus the pressure independent?
Well, it's pressure dependent as far as mechanical linkages are concerned, right? You achieve pressure independence on this solution by using a controller to measure the differential static pressure, compare it to a flow set point.
Oh, I see.
Yes.
Gotcha.
And then you actuate the damper as needed to achieve that flow set point. So we achieve pressure independence electronically here, whereas with the Venturi valve, it's achieved mechanically. That's totally different. So if you want to measure flow, and some people, Tony, love to measure flow, this is the valve for you, and we can give you the straight goods about how to properly apply that valve for your application. But also, if you just love the speed and stability that a Venturi valve can offer, they're very popular for many, many years. This is a great valve as well.
So you've got two solutions. That's good.
Yeah.
So we've got the valves, we've got the controls, the actuators, but then what about the building controls? I see some, some sensors here and some touchscreen controllers. What's going on with all this?
Great question. So we can start here. So this is a This side of our little wall here shows you a typical laboratory with a fume hood control solution. So I would want to, I guess, add at this point that everything you see here, with the exception of a few things, like, for example, the Belimo actuator. Belimo's awesome, we love them. And for example, the sash sensor, everything you see here is designed and manufactured in Canada. So this includes the spun valve bodies, this includes all of the controls, the touchscreen fume hood controller, everything is designed and manufactured in Canada. So the way that this works is when you have a fume hood and you've got a researcher walk up to the fume hood, they're going to adjust the sash to probably some sort of working height. Don't mind the scale of it, it's pretty small here, but you get the idea. You're going to go from some minimum position, call it closed. When they open up the sash, they're going to put their experiment inside.
I love it.
Yeah.
What a great demo.
Yeah, and then you close the sash again when you're done, or they should close the sash. Sometimes they don't. To reduce energy usage. We have solutions for that too. But that's the idea behind this. And so you need something that's very, very fast to respond to those very, very quick, almost instantaneous changes in that open area of the sash travel, right? Because as you start here, your open area is very small. And so the airflow required to achieve that nice air velocity to maintain containment is also small. But as you open up the sash very quickly, you'll notice how fast the actuator adjusts to the new flow set point. And that has to occur because now you've got a large space and you want to keep what's inside that working area inside the working area to keep people safe.
Right, which is one of the advantages of this type of product for labs.
We talked about VV boxes earlier, so you got speed, you've got accuracy, you've got contamination resistance, you really have the whole package.
Great.
Yeah.
Well, Curtis, thank you for the rundown.
I appreciate it, Tony.
Yeah, thank you. We're excited to be the rep now in the Carolinas. So if you're watching this in the future, check the show notes on the YouTube channel. I'll have a link to your website. But if you're in the Carolinas, give us a call and we're glad to support your project needs.